Welcome to this morning's panel discussion, Challenges and Developments in Low-Temperature Solders. Now, low-temperature solders are being used in a variety of applications, ranging from the protection of sensitive devices and advanced packaging to consumer products where they're trying to save a little bit of cost. My panel today is going to discuss some of the challenges and manufacturing issues. I'm joined today by Keith Bryant from Keith Bryant Consultancy, Jennifer Fujokowski from AIM Corporation, and to my left we have Keith Sweatman from Nihon Superior. So thank you, ladies and gentlemen, for joining us today. Let me get straight in with my first question. And that's just really to establish the benchmark of where the current temperature threshold is that defines LTS, low temperature solders.
Well, it's interesting. We had this discussion during an INEMI committee, project committee, and the first definition is anything lower than the temperatures you need for the established lead-free alloys, SAC 305 and SN100C and things like that. So if it's less than that, then we're in the LTS. But I think if you're looking at controlling warpage in IC packages, it looks like under 200 and ideally close to 180. So it depends what the application is as to how you define it.
I would agree and even break it down into a bit further and say that applications between 200 to 190 is low temp, and then even more low temp is between 170 and 190.
Yeah, I mean, I think Intel were the guys who really started pushing this for their advanced packaging side, and they were looking at sub 180, I think, to try and avoid the problems.
Yeah, my vote goes to sub 180.
Yeah, okay. All right. So my next question is of course, many low-temperature solders contain bismuth, and bismuth is known, for being very brittle. So what options are available to make that alloy more ductile?
Sure. So you have a few options. One of the first elements that comes to mind is silver. So that can reduce the brittleness, but will also increase the price. Yeah. So for people who are looking to reduce costs, reduce energy consumption, that might not be their favorite option. Otherwise, you can use antimony, but that'll increase the melting temperature, or you can use something like nickel too. So there's a few options out there.
Right.
Yeah, well, another option is to reduce the bismuth level, because but there's a trade-off with the process temperature, because as you move away from the eutectic, the liquidus temperature moves up. But then, do you have to get full melting when you do reflow? We found you can get very good joints with partial, just even if all the solder doesn't melt. And as you were saying, another thing you can do is break down have a microstructure in which the bismuth phase is smaller or thinner or better dispersed, so that you don't have lumps of it that can crack and initiate failure. So there's a few tricks. I think there's adding things like silver that really goes into reinforcing the matrix, because the bismuth is in a tin matrix, and you can make that tin matrix like a buffer that protects the bismuth phase from the stress that would otherwise crack it.
Right. So you mean like a buffer in the intermetallic?
Well, no. The intermetallic's not the issue here. It's like airbags, something like that. You know that if bismuth gets a high impact loading, it's going to crack. If you can build a little wall around it, and what the silver does is strengthen that wall, and the antimony strengthens that wall through solid solution hardening and things like that, or precipitation hardening, then you've got a little barrier there that will protect the bismuth from the stress that would otherwise crack it.
Now, you mentioned there about the fact that you don't need to have full reflow, and we have this issue where a lot of the solder balls that are on packages are SAC 305, and then you're using a low temperature solder.
The hybrid joint you're talking about, I don't know what your opinion is, but I have a feeling the hybrid joint is not going to survive. It's got too many issues. if you go back to the days when we were phasing in lead-free, for a while you had packages with lead balls and reloaded with a lead-free paste. And in the end, they found that the only way to get reliability was to take it to a temperature where the whole thing melted and you had a homogeneous joint.
Yeah.
So I think the industry is drifting to, well, interesting I use the word drifting towards homogeneous joints, where you have an LTS ball and an LTS paste. And I say drift because one of the issues that we find with the hybrid joints is that after thermal cycling, you find the solder ball has moved. It's actually drifted away.
Right.
And there's a whole lot of reasons why that is. But, you know, these are all complications. Look, it's tough enough as it is without the solder balls moving around. You know, I don't think the hybrid joint will make it to the next stage of low temperature soldering.
I agree. I mean, and I think there needs to be some standard to be brought in to try and help that along. Any thoughts on that, Keith?
Yeah, it's, you know, I'm not an eminent chemist like the people sat beside me, but I mean, we've always known when you're soldering stuff, you know, we always said the best thing to solder was solder. In other words, you know, if it's all exactly the same, then that's the best way that it works.
Right.
But where you've got different LTS materials with different compositions in them, you know, you're not going to get something that's homogeneous, because you're not going to be able to buy BGAs with balls with all of these different things on them. So there has to be a trade-off somewhere.
Right.
And, you know, while I agree, you know, when we started with BGAs, I mean, the balls were pure tin and we were using tin lead to solder them together. The balls never melted, but the solder sort of coalesced up to the ball enough to grab hold of it. And, you know, that was what everybody lived with, because it was the only choice.
Right.
But yeah, I mean, homogeneous is best, but how we do it going forwards, I'm glad I don't have to make those decisions.
Right.
Another aspect of low temperature soldering that uses hybrid solder joints is rework, actually. So when you're reworking joints, you think the most common solder that people have on the rework bench is probably a SAC 305 flex cord wire. So it's kind of like the same. If anything, it's a bit more varied, actually. But that's another aspect of low temperature soldering that, you know, we must consider.
But then in rework, of course, you've got the potential that you're going to then start damaging the sensitive components around it.
Yeah, well, because you have the heat of the soldering iron that you're exposing all of these like temperature sensitive components to around where you're actually reworking.
The other issue with hybrids is that it's been found, you know, there's been an ongoing INEMI project on this, that the ratio of mixed alloy to unmelted alloy or undissolved alloy is quite critical to reliability. Now, how on earth are you going to manage that? If you say, look, the optimum is 30% mixed alloy, and you've got balls of all different sizes on pads of all different sizes, you would have to accurately allocate a volume of paste to every ball that gave you that correct ratio of mixed to unmixed. And I think that's just too hard to do.
Too hard to do, yeah. Okay. So let me move on to my next question. Keith Sweatman, of course, I've got two Keiths on the panel here. But, I mean, can electromigration become an issue with tin bismuth alloys? You're passing.
Take it away. So with low temperature solders, you obviously need to design a flux that is active at those lower temperatures. So, but I think that you can, well, I know that you can design a no clean solder paste with proper electrochemical properties that reduce or that maximize surface insulation values to prevent electrochemical reliability issues.
Yeah, I think Trevor's raising electromigration, a different issue, not the dendrite growth issue from flux residues, but it just is an unfortunate fact that the bismuth atoms dissolved in the tin are very susceptible to movement by the electron wind of current. So you end up with all the bismuth down at the anode end, I think it is. And there doesn't seem to be a good solution to this. Eric Kotz at Binghamton University just presented a very nice paper at this conference talking about this issue. But it does seem intractable. That if you've got bismuth atoms dissolved in the tin phase and a high density current, which you get in some of these processes, the bismuth is going to move. So that's
it's an
another
ongoing
one on
issue.
the list to be solved.
Is it something you run into in the field, Keith? Because you do a lot of work troubleshooting in the field.
Yeah, I mean, from a failure analysis point of view, unfortunately, yes, you see a lot of places where things have gone wrong. And, you know, the whole thing with bismuth itself, you know, it brings an advantage and it brings a lot of disadvantages in the same bag. And it's very hard to monitor. I mean, you know, I've done some work with people who say, yeah, we want to go low temperature, but we don't want to use bismuth. And, you know, that's you know, at the moment, at least, I think a very difficult a difficult way to go forward. And, you know, from what Keith's been saying about the fact that, you know, you can add other things, but then, of course, you have the cost issues and a whole load of other things that come on the back of it. So, yeah, at the moment, there's no sweet, easy, simple solution. And, you know, ultimately, maybe bismuth isn't the answer, but it's the best one we have at the moment.
Yeah, well, I think for a while the EU were a bit sort of anti-bismuth, but they've loosened off since then. But what other alternatives are available?
Well, you could make indium alloys. It's very expensive.
Yeah.
And I mean, they're already being used in some CMOS devices, but it's difficult to see how they could be used for sort of mass electronic production.
Right.
Certainly for low temperature work, you know, people are looking at them for quantum computers and for nuclear fusion. So they're a technical solution, but they're expensive.
They're expensive, but
Yeah.
Okay.
Yeah.
Any suggestions on other alternatives, Jennifer?
Yeah, I would agree with both Keiths in saying that it's a trade-off, right? So it depends on the reason you're trying to implement low temperature solders.
Right.
So if you're doing it to reduce energy consumption and use these less expensive plastic components potentially, then using something like indium is not a viable option due to the fact that it's very expensive.
Right.
But if cost isn't an issue, then it does make sense to use a bit more of an expensive element.
Okay. I'll put my next question to you, Keith, over are LTS alloys, generally speaking, cheaper?
Yes, in theory they should be. Anything that doesn't have silver in it, by definition, it's going to end up cheaper to make. But it's like everything. Sometimes when it's new, it comes out at a premium price because it's new and a better solution.
Right.
But yeah, in reality, you know, anything without silver in is going to be cheaper than stuff with silver. So.
And also, bismuth is cheaper than tin at the moment. We have a lot of customers making consumer appliances where they're using tin bismuth because it's cheaper than any lead-free solder.
That's true.
Yes.
And they don't care about whether it cracks or breaks.
No, they do care.
Well,
but
yes.
in that application,
Right.
it's good enough. You know, they still get reliability because your rice cooker or your microwave oven or something is not getting the stress that a laptop computer might be getting. So there are some places where it's just used because it's cheap, cheaper.
Right. Okay. All right. Back to you again, Keith, on this one. Just my last question: what manufacturing and quality issues should operators be aware of when using LTS?
Well, all the ones that we've talked about so far today. And obviously, if you're putting something into a harsh environment, then you really have to worry about cracking and a whole load of other things. But issues that we've also seen is second side assembly with low temperature solders. Again, because it's not getting up that high the first time, a lot of people are having issues that the board, after it goes through the second side, the stuff that's hanging down is maybe not as good as it should be.
I see. That's interesting.
The point that emerges from that actually is that because of the issues of using LTS for the whole board, say a computer motherboard, people are reluctant to do that just because there's one component that warps heavily. So there is a trend now to do most of the board with regular lead-free and then just come in and do that package with LTS.
Exactly.
But means you can't print the paste, so you have to go to the fairly new but still well-developed technology of jetting.
Yeah.
You jet into there. So it means you need a different sort of solder paste than what you would use if you were printing.
That's right.
Because the characteristics that you need for good performance in jetting are rather different.
Yeah,
So
you've essentially got to move up a paste size, I would think, to be able to do the jetting.
a different
Down
rheology.
paste size,
Different
yeah.
rheology.
Paste size and a different rheology, but
Yeah.
I'm just wondering how you reflow it, because you've got a material that wants a high temperature and then you've got a low temperature material. You can just focus in with a laser or something and just heat up that part. Ah, that's neat.
Yeah.
Interesting.
I mean, it might only be a transition stage. Maybe in the near future, people will feel comfortable enough to do the whole board. But just at this stage, step by step.
Right.
Those who have done the whole board have found they've had to come in and plaster it with reinforcement so that it survives drop testing and things like that.
Right. Okay. Finally, to you, Jennifer. Any last-minute tips on manufacturing and quality issues for operators?
Yeah, so quality issues are solved by, again, like reworking your product. So when it comes to rework, I mentioned that a lot of people are using that SAC 305, like flux cord wire. And something that isn't really thought about is using low temp as the rework alloy, but something that's actually prohibitive in the soldering manufacturing side is, we were talking about bismuth being so brittle, and what flux cord wire really is like a metal tube with flux injected into the middle, which is based on a continuous extrusion process. But since bismuth is so brittle, that slows that process down. So it makes the availability of low temperature flux cord wires pretty limited and quite expensive. So that's like the soldering manufacturing side of things, which then affects the end user, because those low temperature flux cord wires aren't as available to them. So that's just something to think about if you want to use an entirely low temperature solder assembly, that you might end up using maybe a solid wire and an external flux and start mixing a lot of chemistries and having new material considerations.
It's a really interesting observation. I mean,
Well, the other thing is you can make the wire, the flux cord wire, and it's bendable. So if you're using in robotic soldering, when it's fresh, but you leave it on the shelf for a month, and the scary thing about tin bismuth alloys is that they are at a high homologous temperature. At room temperature, diffusion is happening very quickly. You get precipitation effects and whatever, and when you take the reel of wire off the shelf to do another run, it falls apart in your hands because it's in-brittle.
yeah, so it's going to have all sorts of storage. You're going to be very careful with your storage conditions and handling and everything else like that.
Yeah, so it's just a trick that you're dealing, the other solders are very stable over time. They're the same 20 years later as they were when they were made. Tin bismuth, it's different next week from what it was last week.
Right, okay. Well, there we go. We've discussed some really important issues around the topic of low temperature soldering there. So I think we've pretty much used up our time today. I want to thank our panel, Keith Bryant from Keith Bryant Consultancy, Jennifer Fujilkowski from AIM, and of course Keith Sweatman from Nihon Superior. So thank you to all my panelists, and thank you for watching today.
Global SMT and Packaging opens the windows of the world to bring you the latest news and technologies from Munich, from Bangalore, from Shanghai, from San Diego.